Why is water an excellent solvent for most ionic and polar covalent compound, but is not an excellent solvent for nonpolar compounds? So this has to do with the energetics of solutions. Here's energy, or enthalpy, you can say. So the dissolution process occurs in three steps. You can say we need to expand delta H, or the enthalpy needed to expand the solute, and we need to expand also the solvent. So those are both endothermic processes. They require energy because you're separating things that want to be attracted to each other. Okay, so water's polar, they're attracted to each other, so you're going to have to put an input of energy to expand them. And the same thing with a solute that is ionic or polar, they're going to be attracted to each other, so it's going to require a significant amount of energy to separate them. All right, if it was nonpolar, then the delta H of expanding would not be as extensive. All right, so once they're expanded, then you have this delta H of mixing. That's exothermic because now they want to be next to each other, the expanded solutes. So if this is like an ionic compound, something like that, then all the water molecules are going to be surrounding it, and they have this ion dipole attraction now, and that's much more stable. So that's going to release energy. So that mixing process is exothermic. Well, here's the bottom line. When you have a solute that has similar intermolecular forces as a solvent, this mixing is going to be significantly exothermic. So your overall heat of solution, or enthalpy of solution, is going to be close to zero, or maybe even negative, which would be even better. When that's the case, you have a good chance that a solution is going to form, that the solute is going to dissolve in the solution. Short answer, like dissolves like. And when we say like, we're referring to polarity. Similar intermolecular forces dissolve in other solvents with similar intermolecular forces. All right, and it has to do with this, the energetics here.